Hi, I'm Maura Enright, and I'll be talking about Newton's laws of motion as well as forces today. We'll start off with Newton's laws of motion. So first we have his first law, which is inertia. Newton's first law is only valid in non-accelerating inertia frames. Inertia basically means that something has a tendency to stay at rest unless acted upon by another force. Newton's second law would be F net equals ma. So F net is the total force acting upon an object. M is the mass of the object in kilograms, and acceleration would be a. Newton's third law is equal and opposite forces. So for instance, if I were to push on a chair with 25 newtons, the chair would be exerting an opposite force of negative 25 newtons on me. So now that we've gone through the basics of Newton's laws of motion, we can move into forces. There are 5 major types of forces, the first being gravitational force. Gravitational force is mass times g. G is the gravitational constant, which can be calculated when outside of the general realm of the Earth. So for our purposes, it would be 9.8, and on the AP test, sometimes they do 10. The second force would be normal force. So normal force is basically almost the same as Newton's third law, assuming that you're perpendicular to the surface, basically. So if this was a surface and I was sitting on here and my mass was 10, you'd do 10 times 9.8, 98. So my force is 98 on the ground. So the normal force would be the force the ground is exerting back up on me, which would be 98, equal and opposite. However, if the surface would be on a tilt, then you would have to do a free body diagram. Now I'll talk more about free body diagrams later, but basically you're taking the angle that it's at and using that to calculate the exact forces to make sure they are equal. The third force we have to talk about is frictional force. So we all know friction from just, layman term. Before physics class, you never really used it to calculate. But the equation for frictional force is mu times n. So mu is a constant. Every surface has a frictional constant, one being static and one being kinetic. So if something is being acted upon by the frictional force, it is unable to move because of the static coefficient. However, if it begins to move, the frictional force is still acting upon it, but you now use the kinetic coefficient. So the fourth force that we can take into account is tension force. So that's basically if you have a rope attached to something and you're pulling with the rope, the tension force would be the force the rope is applying. And the tension force is always along the rope or along the axes. So, and our last force we have to take into account is spring force. That is K times X. So now, and K is also a constant for any spring, so you'd be given that in any equation. And X would be the displacement from equilibrium. So if a spring is at rest and sitting, that would be its equilibrium position. If you were to push it that way, the X would be positive. If you pull it out, it would be negative, because the acceleration would be in the direction. So now that we've gone through all the basics, we can start doing some basic practice problems. So let's say we have a box. The box is 5 kilograms. So we've got our 5 kilogram box. We'll start with it just on the surface. So if we want to do a free body diagram, free body diagrams are pretty basic. You just do a dot, so this represents our box. Then you want to draw any force that is acting upon this box. So this box is on the surface at rest. So the only forces that are really acting on it is we can assume the force of gravity, which would be m times g, and then the normal force from the surface is in this direction. So we have normal force. Not bad, right? So now if we want to start acting upon it in any which direction. So let's say we want to push it to the left with 10 newtons of force. So we'll give that a 10, and you want to draw that over here. So because you can see that the forces in the x direction are not balanced, you can predict that the object is moving in that direction and is also accelerating. So that's when you apply the F net equals ma. Because the y is balanced, you don't have to look at mg or normal. All you have to look at is this 10. So we know that the box is 5 kilograms, the force is 10, so the total force in that direction is 10, equal to 5 being the mass times the acceleration. So if the problem asks you to calculate the acceleration of the object, you know it's moving with a constant acceleration of 2 meters per second squared. Whenever you do calculations for physics, that's always going to involve meters and seconds is usually the way you would do calculations. I'm now realizing the numbers are backwards on the board because it's going to reflect it or whatever, but you still see what I'm doing. So that's a pretty basic physics question. Now if we want to get more complicated, which is what I was bringing up when we were talking about angles, let's say we have that same box on a ramp. So we'll start with the ramp not having any frictional force or any frictional coefficients. So you've just got your box on a ramp. It is 5 kilograms. So the force of gravity is always going to be straight down. So if you were to draw your free body diagram on this, there's that force, but the normal force is in this direction. So if the surface is frictionless and you're going to assume that the box is going to start sliding down in that direction, the question is, how do you calculate that? Because the force, if you're looking at the axes, is not directly on the x or the y plane. So this is where you have to apply your knowledge of trigonometry. So if you have the angle from the axes, so let's say that is, what do I want to use? It's an easy angle. We'll just say it's 45, right? And you want to find the amount of this force that is acting along the axes upon which the box will travel upon. You're going to do F cosine, because that's the adjacent side, cosine 45 degrees. So once you have that, you can assume that the normal force would be balancing out the part of this force that would make it move along the y-axis. So now you can take the F cosine 45 and set it equal to the mass times the acceleration if you want to solve for the acceleration. So now that we've done that, we can start plugging in numbers. So why don't we give, if we have 5, so the force acting in this direction is m times g. However, so if we were to plug in mg cosine 45 degrees is equal to mass times acceleration, using basic laws of algebra, you can cancel out the m's, which leaves you with a is equal to g cosine 45 degrees. I don't have my calculator with me, but that's basically the gist of the problem. The only way that this problem can be made slightly more complicated is if we were to add a frictional force into this problem. So, we'll erase this and we'll